Okay, the record is now on. So let's come back to this problem. Okay, as I mentioned before the record, that is, if it's a beam, you actually have so many choices to calculate the displacement. But if it's a frame, it's almost impossible. Now you're going to be down to just the virtual work method. Okay, and I just realized that for this structure, actually I used the moment area method because it's a cantilever beam, and if you are going to use the virtual work, you realize that you would have three moment equations, because this is one equation for this, another for this, and then another for that. So in this case, say to use the virtual work would be kind of difficult. And let me try to finish off this problem by using the moment area first. And if you want to challenge yourself, or if you want to challenge me to do the virtual work, I can do that. It's not a big problem. But from now on, let's make sure that we achieve what we set out to do. That is to analyze this structure for the, what does it say here? Shear force and bending moment diagram. Okay. So step number 3 is the calculation of deflection. At C. Now this is of course due to the actual load. Okay. Okay. So if this is our primary structure here, if this is our primary structure, this is our target, and you should know that the calculation of the displacement at C, this one, by using the moment area is really simple, because if you can recall, this say delta C is going to be equal to TCA. Okay, so if I am going to do it by the moment area method, I must draw the bending moment diagram. And what do we have here? We have the 1 ton moment. Okay, it's going to be constant like that, right? And then 5, you have the length of 3 meters before the support, and this 5 is going to create moment equal to 15, right? So that becomes 16, minus 16, and then minus 1. Can you follow that? And I better remove the support so that this is really the bending moment diagram. Got to change the size of the rubber. Okay, so this is the bending moment diagram. But if you want to use the moment area method, this becomes the M over EI diagram, right? So that's the one. And now you can see that things become very easily. Delta C, oops, deflection is also one. Delta C is equal to T CA, and that is the moment of the area of your moment diagram between A and C with respect to C. And then from A to C, it is going to be this area, right? Okay, to stop at C as well. Okay, and without further ado, say this is going to be equal to 1 over EI. I'm going to break this into one long rectangle, okay, and then one triangle. And that's going to be the area of, and let's say to help you guys a little bit, let's paint this with different color. Okay. So this is going to be equal to 1 multiplied by 6 minus 1 multiplied by 6. That's the area of the yellow one. I can paint this. Okay, that's the area. And we take moment with respect to C. So the moment arm is 3. And then the area of the triangle, it's a half of that length, I believe, is 3. And this height now is 15, right? So it's 15 minus 15. And we take the moment with respect to point C. So that is going to be our moment arm. So that's 5. And to help you see better, this is this. Okay. So it's easier. And this is minus 130.5 over EI. If you want to do the virtual work, wow, that's going to be something. But let's say we can do it. You want me to do the virtual work? Yes or no?
Yes. Yes.
Okay, so let's try to do this. Okay, virtual work. Because our point of interest is at C, so we can hopefully simplify our structure a little bit, because here you're going to have moment, because that moment is constant. Okay, and let's say we have the, excuse me, okay, A, B, C, trying to use the same nomenclature. So A, B, and C here, that would be easier to, again, try to write our moment equation from the open end. So the big M, oh, sorry. Okay, so the portion, you have to use portion now because it's not a member. BC, the big M is going to be equal to -1. Am I right? And our virtual small m is -x. Range is how much? 0 to 3. Now, I can actually see this bending moment diagram, you know, and try to think about how to write the equation. But again, if I want to maintain the same equation for my virtual load, portion AB, if I want the same equation here, this one must be from 3 to 6. Okay, so I must look at this big M and try, oh, not enough space. Okay, and for my big M now, if I am going to begin the range from 3, my moment equation would be -1, oops, -1 minus the load, which is 5, and then x minus 3. That would be my equation. Do you agree? Not the only, just to substitute the x equal to 3 and 6 into the equation and see what we have. Okay, and when I plug in x equal to 3 here, the second term is 0, so I have -1, which is correct when we look at the value of the moment here, -1. And then when I substitute x equal to 6, now I have 6 here, 6 minus 3 is 3, and 3 minus 3 multiplied by 5, that's -15, -1, -16, so that's correct. So that would be my equation. So the virtual work would be integral from 0 to EI is constant, right? 0 to 3, -1 minus x plus from 3 to 6 -1 -5 x minus 3 multiplied by minus x. I forgot to write dx over ei. Okay, sorry about that. Dx over ei. Hopefully, you're gonna get the same number. But that's the virtual case. Okay, and that is also the actual, not actual, the deflection of your primary structure under the actual load. Okay, so now we move on this. Step number 3, right? So step number 4 now. I remove this. Or before I forget, you can redo this problem by yourself by removing MA instead and see if you can match the result. Okay, that would be the good exercise because you already know the answer. Now I have to apply the unit load here, and of course this one is going to come down, and I am looking to obtain delta at C due to load at C, delta CC. Okay, and again, if I proceed to use my moment area, that would be my bending moment diagram, and my delta, see, that's the sim. You guys still can see the screen, right?
Yeah.
Okay, it's a symbol of the iPad going low on memory. It's like my delta CC is also equal to TCA, and this is the area. And it is going to be equal to 1 over EI. The area, if that is load is 1, so you have the length of 6 meters, right, to the support. So this is -6. The area of a half multiplied by -6, and the length of the base of your triangle is also 6. And now, because we need to take moment at this location, okay, that's the because the length is 6, and that is 5. 4, not 5. 2/3, that's 4, right? Yeah. Okay. Okay. So that's 4. This is -72 over EI. And if you want to do virtual work, it's going to be pretty similar to this, right? But this time you have it easier because you just one equation, and then the range is from 0 to 6. So virtual work is also easy in this case. Delta CC is equal to integral from 0 to 6 minus x dx over EI, and easily it should come out equal. Very easy to calculate here. X cubed over 3 EI from 0 to 6. Okay, that's 72 over EI as well. So it's the same number. Okay. All right. So now we have this. It means that we can go to step number 5 to I should write the step number, maybe. Okay. Step, oops, sorry, I'm sorry. This is the, oh my, the iPad is going berserk. My iPad is pretty new, you know. Deflection delta CC. Okay. So step number 5 is compatibility now. So now you have to be mindful of the symbol a little bit. Okay. So now delta C plus delta CC. Remember that I calculate everything by using a unit load. So I have to multiply this with RC. This is equal to 0. So simple enough that for the number that I use with moment area method, both values are negative. So pretty slow, so bear with me. The iPad is going berserk and it doesn't seem like a good idea to restart everything now. Okay, so minus 130.5 over EI minus this number, because it's negative, 72 over EI multiplied by RC, that is equal to 0. So RC is minus 1.8125 tons. It's negative because I apply the unit load downward. So it becomes negative. This means that it's upward because the sign is negative, which means it's the opposite direction of my assumed unit load. Okay, so after we get this, the rest should be a piece of cake. Okay, so now you have a structure with the known force now. Now it becomes the known force. Oops. Okay, now you know this. One moment. Okay, and we also have the 1 ton meter, and we have a 5 tons here. Okay, so this case the loading condition is not very simple. So in this case, you may not be able to guess the deflected shape very accurately. I maybe can guess that this is the downward moment, so this part is going to come down like this. And maybe this load is so heavy, so you can go, like that before it goes back to 0. So we have like 2 points of inflection. Is that possible? We will only find out after we perform the analysis and obtain the shear force and bending moment diagram. Okay. So with that, you can use sigma Fy to calculate the remaining reactions. Force that has to be 3.1875, right? So that in the end it's 5. But for the moment, you have to perform the calculation. So sigma MA equal to 0. Now you have the you can also do this very straightforwardly by, okay, it's 5 multiplied by 3 plus 1 minus 1.8125 multiplied by 6. Or to make it more interesting, okay, you can go back here and oh no, it's not the okay, that's it. I thought I would give you something more interesting, but let's not do that. It's going to become too complicated. So that's it. Okay, and the moment here is, oh, here we go again. 5.125 ton meter. Okay, so after we have this, the shear force and bending moment diagram is only a matter of minutes away. Going up like that, coming down like this, and then 0. Remember, there's no shear beyond that support. This is 3.1875. This is minus 1.8125. And your bending moment diagram is going to be a negative here of minus 5.125. And you have the positive area here. Okay, use that area to obtain the value, and the area is equal to 3.1875 multiplied by 3. Incidentally, that is greater than minus 5, right? So you're going to have positive moment. Yes, point of inflection. And whatever that is, you're going to have, you know that this is going to be minus 1, correct? That has to be minus 1. So whatever you have there as the second area must bring your moment diagram down to meet with this value, correct? So that is it. Okay, and you therefore have 2 points of inflection, and okay, that is where it is. So go back to your deflected shape. That's where it should be, and then this. So it's probably that one. Okay, so this is the positive curvature, and then it returns to negative curvature here. Okay, and that is a negative curvature. And now, because there's no uniform load, to obtain the point of inflection here should be a piece of cake, right? And let's see, right here, this point is simply 5.125 divided by 3.1825. Okay. And the maximum moment here, M positive max, after this area turns out to be 4.4375. Okay, and you can use that number to try to locate this point of inflection as well. Okay. This would be 4.4375 divided by 1.8125. Okay, so then that's it. We're done with this problem. Is there any question? Hello, are you asleep? Still alive?
I have a question.
Yeah, go ahead, ask me.
At the fourth step for the virtual work, how the equation came from?
Well, this is incidentally the same. You mean this one, right?
I mean fifth. Sorry. Yes, that one.
Yeah. I didn't show it in details because we did it here. It's the same as this one. See? We want to know the displacement caused by the unit load, right? Which we already did this, but this time it's just like in the previous work. This time your actual load is just equal to your virtual load. So it just, slightly confusing maybe. I don't want to use that word, it's so negative. But this is the actual. And it is also the virtual. Okay, because it's just like this. Because this is your virtual, right? when I demonstrated the virtual work to you, I drew the equation for the actual load case and then the virtual load case. But if you look at the situation where you want to calculate the displacement due to the unit load, your unit load also becomes your actual load. So that's why I can easily bring this to work. Okay, yeah, I was very quick in that step. So it's good that you ask. Otherwise, you would miss this. Okay.
Thank you, Khab.
Okay. So is there any more question? The involvement is a little bit better today, so I can say I'm a little bit more happy. Or I should say happier, right? Is there any more question? I guess not. So yeah, we have done so many examples today, and we revisited the two examples, or three actually, where I introduced you to the concept of the virtual work, the two beams and then one frame. Then we did this. So that's this is the fourth problem for today. Here we go again. The screen sharing is gone. So the fifth time, right? Can't believe it. Oh. Okay. I really, I don't think it's a very good idea to carry on, because I think your mind must be very, very tired by now. But we have more than 10 minutes left. So if you don't ask me anything in particular, if you don't request that I repeat some things that you may not get the whole picture of, I have to march on, See, we have more beams. See that? Okay. And you should know that I have given you a lot of exercises on the calculation of virtual work, and I wanted you to have the active session in the past holiday, but because it was a holiday, so not many people showed up, and so you guys have to find the time to review the virtual work now. Can I scroll up, please? Yes, I can. Why don't you say it out? Your voice. Is that enough for you? Okay. Okay. All right. So let's say let us wait for a minute or two for some of your friends to catch up, because if it was me, I would prefer to write the notes down myself, even though we have the video clips, even though I write everything here that you can see, it would still be better for your concentration to try to, follow the content by writing. So give it a minute or two. If you don't ask me anything, I don't want to waste 10 minutes here. So I'm just gonna.
Teacher,
Yes.
Can you go to the step number 3?
Step number 3 coming up. There.
Yes. But
Okay.
in the list, I'm confused about in the number of 3 or 5 is come to teacher.
3 or 5.
Can I write it? Where is?
Yeah, you please.
Very confused. Can you repeat
okay.
this?
Yeah, it's a
again?
moment diagram. So I try to help out by painting the color yellow. So this is the yellow is the area, right? And the 3 that you mentioned would be the distance from the centroid of the yellow rectangle to point C. Okay, because it's the moment area method. You need to take moment of the area, right? So the yellow one is the area, and number 3 is the moment arm of the yellow area incidentally. Okay.
Oh, use centroid, right?
And hello, yeah, kids having online classes. What a blessed. I am truly blessed. Yeah, it's so noisy today, and they had a quarrel. Yeah, it's a very good idea to have kids around, right? Guys can see that now. Okay, so you have any question? This one? Any more question? You know, I have to say my apologies to the way that I use the moment area method. It's not really the focus of the class, and I didn't look to my old example thoroughly, because I just wanted to include as many examples as possible so that you can see how things are developed. And then I realized, wow, actually it's a moment area. But in fairness, I try to also do it with the virtual work. So if you wish to carry it out, you can do so. We already have the equations, so and so, okay? Oh, good gracious me. Now it's even crazier because, yeah, that's it. I took another example from the, this was done how many years ago? Maybe 15 years ago. And the next one, I did it with the conjugate beam method, crazy enough. So I'm not going to do that conjugate beam method for you, but this problem, it's like, you know, the part of it is just to demonstrate that sometimes using the conjugate beam is better because we have so many point loads, and you know, your moment diagram is going to be chopped into pieces. But yeah, I suppose we can use the virtual work, or you can, you know, try to remove some other reactions and see what happens. Okay, but you know, it's my own preference to remove the reaction in the middle, because now that I would have a simple beam, it's pretty straightforward. So because we have a few minutes left, so let us try to see what you need to do with this problem. Okay, we may not have to carry out the calculation until the end, but just to make sure that when you see a problem like this, do you now grasp the concept of what you need to do to solve this? Okay, so yep, say step number 1, determine that this structure is, of course, the indeterminate with 1 degree of redundancy. Okay, and let's say I may call this point A, B, C, D, and E like this. So my step number 2, I'm going to create the primary structure out of this. Right now, you can, yeah, are you comfortable with this now? Junior, please. I know senior should be, except the senior who just taking this class for the first time. Primary structure, I decide to remove RC. So my primary structure is going to look like this. It's a 16 kilonewton, and that is 20 kilonewton. Okay, and the result of removing reaction at C would mean that we now going to have delta C. Okay. Wow. To calculate delta C by using the virtual work is really troublesome. Okay. Anyway, we will march on. I don't have any plan to do it, but let's say if we are going to do it, calculation of delta C is up next. You may want to use the virtual work to do it. And if you say, if it's gone again, you believe that? I don't believe it. Why Tuesday is always troublesome? Hang on. Okay. So if we are going to use the virtual work is to be used, you are going to have to apply the straight enough. Right there at C. And calculate the displacement or write the moment equation here. Okay. But then this is we are in the zone where we need to calculate the delta C by using the virtual work. So you apply the unit load there. Okay. But then if step number 4, look at that. The calculation of displacement due to RC, right? So this step becomes the similar step as they're using the virtual work. So it's the same thing. That's why it's gone again. Okay. Let me try to finish this, okay? And then that's it for today. No calculation on this. Takes forever. So you can grasp the idea, right? That we need to apply, we need to use that unit load to calculate the displacement due to the reaction. I don't understand what's going on here. It's gone. Okay, let's try it one more time. And then it's gone. So I can't reconnect. Oh, it's back. Last. So if we are going to calculate the displacement due to RC itself, we can again repeat this. Okay, so this is when your actual load and virtual load are identical. Okay, we do this, and then we can set up the compatibility in the end. Okay, and that will be the end of our calculation. It's gone again. You can't see the word compatibility. So, okay, you can leave this problem as your exercise on Friday as well. Okay, I'm not gonna go back to share it again. It's just so troublesome now. I don't know what happens. I think the iPad is low on memory. That's why it crashes like all the time. And it's just, I haven't done anything. So 3-hour class means iPad wouldn't survive that long. Huh? Anyway, any question? You, especially junior, you now know that you need to go back and try to review the virtual work method. Okay. No. And you don't have much time. And then when you come to the active class, you guys leave first. Okay.
Yes.
Yeah. So a handful of you are just doing just fine, but I worry about the rest. Okay. Is there any question? Any more question? You know, I don't know if you're going to have a question. If the time is pretty much up. So for those of you who do not have any questions, you guys, please feel free to leave. For those of you who have questions, you know, you can try asking now. I am going to try to restart my iPad. Okay. In the meantime, just wait like a few seconds. Any more questions? No. Any more questions, folks? Okay. Well, I'm not worried about senior much, you know. Okay. What about junior? Hello. Okay. See if that's the real case for the problem. Just want to know. No, it's not coming back. Wow. Is it the internet? Oh. Okay, if you don't have any question, then that's it for today then. Unable to connect. No, it's at the at least it is dead when the class is over. Geez, I don't know what happens. Every Tuesday. Monday is fine, Thursday is fine, Tuesday messed up. Okay, so I'm gonna stop the record now then.